the United States of America was suddenly and deliberately attacked by naval and air forces of the Empire of Japan. Last night, Japanese forces attacked Hong Kong. Last night, Japanese forces attacked Guam. Last night, Japanese forces...
A year after Pearl Harbor, the Pacific Fleet of the U.S. Navy was still highly vulnerable to attacks by Japanese dive bombers. But in January 1943, thousands of workers in the U.S. began producing a new high-tech secret weapon, the proximity fuse. Small enough to fit into an anti-aircraft shell, the fuse eliminated the need for a direct hit by detonating the explosive when it neared the target. At the heart of the fuse was a miniature radio transmitter and receiver, using a remarkable new invention, the subminiature vacuum tube. This tube represented the latest step in the rapid evolution of radio technology, an evolution during which basic science, innovative engineering, and the demands of the military and commercial marketplaces created a new industry. In 1865, James Clerk Maxwell formulated a mathematical theory which proposed that a changing electric current would produce an electromagnetic wave. He predicted that this wave, composed of fluctuating electric and magnetic fields, could travel through space at the speed of light. How such a wave could travel through empty space defied explanation and eluded experimental proof. 23 years later, in 1888, Heinrich Hertz performed the historical experiment that demonstrated the existence of these electromagnetic waves. Today, we use a broad spectrum of electromagnetic waves in our daily lives. On December 12, 1901, at Poldhu, England, Guglielmo Marconi made radio history. Using a 25-kilowatt spark transmitter and a giant antenna, technicians began sending the letter S in Morse code. Across the Atlantic at Signal Hill, Newfoundland, Marconi and his assistant George Kemp listened for the signal. Marconi was already famous as the inventor of the wireless telegraph. An engineer and entrepreneur, he was now ready to challenge the cable companies. In a howling gale, Marconi and Kemp launched a kite carrying an antenna to 400 feet. At 12:30 p.m., Marconi heard the three dots sent 2,000 miles from England. But radio technology was poorly understood at the time, and transatlantic communication proved unreliable in comparison with existing cable technology. Consequently, Marconi's wireless telegraph business remained limited to marine communication. Seeking to improve radio communication, engineers and scientists from all over the world searched for better detectors of radio waves. In 1904, John Ambrose Fleming, an English scientist working for Marconi, found that a lamp invented in 1884 by Thomas Edison could detect radio waves. This lamp acted like a one-way valve that could transform the oscillations of radio waves into a steady flow of current. Back in America, engineer and entrepreneur Lee DeForest was also searching for a better detector of radio waves. In 1906, he improved the sensitivity of Edison's two-electrode lamp by inserting a third electrode, the grid, to control the flow of current between the filament and the plate. Since a small change in the grid voltage produced a large change in plate current, the tube could act as an amplifier, making it possible to boost very weak radio signals. Called a triode because of its 3 electrodes, this device made all other detectors obsolete. Later, in 1913, another American engineer, Edwin Armstrong, found that tubes could also transmit radio signals. Aided by advances in circuit design, metallurgy, and vacuum technology, vacuum tubes dominated radio technology until the 1950s. Although vacuum tubes represented a technological breakthrough, their transformation into practical and reliable products and their success in the marketplace arose from military and commercial demand for radio equipment. The outbreak of World War I created the first massive demand for tubes. In the U.S. alone, over 1 million tubes were manufactured for the armed forces. After the war, the beginning of commercial radio broadcasting set off another surge in demand for tubes. By 1923 in the United States, there were 583 broadcasting stations and 5.5 million radios in homes.
America's first radio station.
And even before broadcasting, the amateur radio operators who pioneered shortwave communication numbered more than 11,000 in 1921. As tube technology advanced with the expansion of radio, entrepreneurs found other commercial applications for vacuum tubes. For example, in the late 1930s, companies in England and the U.S. began producing subminiature vacuum tubes for hearing aids. Norman Krim tells how in 1939 he started the subminiature tube business for Raytheon.
So one of the projects that I did a little market research on for Mr. Marshall was would there be a market in the United States for hearing aid tubes, and would it be large enough to justify Raytheon's entry? One of the things we had to be careful about is if we chased too many new ideas, we didn't have the money or the people to carry too many things through, so we had to concentrate on what we thought would be the winners. Well, after I studied the situation, I wrote a report for him, and my conclusion was that there would be a pretty good market, and we should stand a pretty good chance of entering that market and being successful. So I went to Marshall, and I told him that after he read my report that I thought this was a pretty good field to enter. And he looked at me very sternly. He had big, heavy, shaggy eyebrows. And he said, "Do you know what you're doing?" And I said, "Yeah." He said, "Well, how much money will it take to get these tubes to the market?" And I told him it would take about $25,000. And he finally said, "Okay, if you agree that I can fire you at the end of a year if this thing is not a success, I'll go ahead."
Raytheon developed a smaller and more reliable tube, which took less battery power than its competitors. It soon captured the market, and sales of new compact and portable electronic hearing aids shot up from 50,000 to 300,000 a year. These same tubes were the critical component of the proximity fuse, a novel idea developed as part of the war research effort. In 1940, under contract to the National Defense Research Committee, Raytheon and government scientists redesigned the tube to withstand the shock of 20,000 times the force of gravity.
They would shoot the tubes out of guns and find out where the tubes failed. They get that information back to us, and then through Dr. Mimlin at Columbia, working with Dr. Weeks, who was our chief engineer, Alan Rockwood and Ross Wood, and later Margaret Bassett, they kept redesigning the parts as they failed until we came up with a structure that would withstand 20,000 G. And it's something that we could manufacture in very high volume and with very low scrap rate.
The high-tech fuse knocked out the V-1 buzz bomb, decimated the German army in the Battle of the Bulge, and protected the American fleet from kamikaze attacks. Historians maintain that the proximity fuse ranks near the atomic bomb and radar in military importance. After World War II, the tubes found application in handy talkies, pocket radios, guided missiles, instrumentation, and other devices requiring miniaturization. In the U.S., workers at Sylvania and Raytheon plants produced over 100 million tubes for the military during World War II. Up to 1986, workers at Raytheon, using original manufacturing equipment, were still producing subminiature tubes for military use. But in 1948, the vacuum tube business met its greatest challenge. William Shockley, Walter Bratton, and John Bardeen of Bell Labs announced the invention of the transistor. Norman Krim realized that the transistor would be a major threat to the tube business.
So I wrote a paper on the future of the transistor if certain problems could be solved, and we agreed to follow that very, very closely as something that might be a threat to our hearing aid tube business.
By the late 1950s, it was evident that the tube could not match the advantages of miniaturization, reliability, and efficiency offered by semiconductor technology.
Well, there was always talk about that the tubes were going out, but they had been saying this for maybe 30, 35 years, but it's finally reached that stage, and I think nobody really wanted to accept this because we had heard it for so long. But now we realize that it really has finally come to that stage that it's gone, and we're very sad about it because it's a part of our life and it's contributed a lot to our life.
Raytheon shut down the last major production line in the world in Massachusetts in February 1986. The closing of this production line marked the end of an era. Subminiature vacuum tubes, once an innovation at the leading edge of electronic technology, could no longer compete. From theory to radio to vacuum tubes to semiconductors, the cycle of technology and human invention has forever changed our lives. We can't be sure where these cycles will take us. We can be sure only that they will continue.